So as promised, in this part of the lesson I'm going to talk about linear modeling, and Anne's going to finish this lesson talking some more about linear modeling. Let's look at an application. Some office supply stores sell copy cards to their customers for use in the store's copy machines. In this activity, we'll explore models that give the value of a copy card V in terms of the number of copies made N. The first model is given by the equation V equals 10 minus 0.1 N. The graph of this equation is shown in Figure 1. What is the practical significance of the vertical intercept? Well, looking at our graph here, we can see that the vertical intercept is the point 0, 10. And we were told about our model. We were told that V represents the value of the copy card. We can see that label on the vertical axis. And that N represents the number of copies made. We can see that label on the horizontal axis. So in the ordered pair 0, 10, 0 corresponds to N, the number of copies made, and 10 corresponds to V, the value of the copy card. So we can say that the vertical intercept (0, 10) tells us that the initial value of the copy card was $10. Well, what's the practical significance of the horizontal intercept? Looking at our graph, we can see that the horizontal intercept is 100, 0. So the N value is 100. The number of copies made is 100. 0 corresponds to V. That tells us the value of the copy card. So the horizontal intercept (100, 0) tells us that when 100 copies are made, the value of the copy card is $0. What's the practical significance of the slope? Well, thinking about the vertical and horizontal intercepts that we just looked at, to get from the vertical intercept to the horizontal intercept, it looks like we have a rise of negative $10 and a run of 100 copies. 10 over 100 is 1/10, which we can write in decimal form as 0.1. So we have negative $0.1 per copy. Now, if we'd been paying attention, we could have looked at our model. Our figure number reminds us that the model is V equals 10 minus 0.1 N. This model is in slope-intercept form, so the coefficient of N here, the negative 0.1, tells me the slope. Same thing I got by looking at moving from the vertical intercept to the horizontal intercept. So what is this slope telling us? Looking at our line, we can see that the line is decreasing. The value of the copy card is decreasing. The slope's telling us how the value of the copy card decreases. So the slope, negative $0.1 per copy, tells us that the value of the copy card decreases at a rate of $0.1 per copy. We could also say that the value of the copy card decreases at a rate of 10 cents per copy. Well, let's consider a new model, V equals 20 minus 0.1 N. Give a verbal description of how the graph of this model will differ from the previous case, and discuss the practical significance of this change. So let's remember our previous case. We just looked at the model v equals 10 minus 0.1n. Now we're considering a new model, v equals 20 minus 0.1n. So we just discussed the slope of the previous model. The value of the copy card was decreasing at a rate of 10 cents per copy. Well, the same thing's happening with our new model. Notice that the slope in both of these models is negative 0.1. We're asked what's different, though. Well, our value of 10 in the first model told us about the vertical intercept, 0, 10. In this new model, the value 20 tells us the vertical intercept is 0, 20. So in our new model, we have a different vertical intercept, 0, 20, which means the initial value of the copy card is $20 as opposed to $10 in the first model. So the new model has 0, 20 as a vertical intercept. So the initial value of the copy card is $20 as opposed to $10 in the first model. Well, let's talk about how the graph of the new model confirms our observations. So in this figure, let's start by looking at our first model, v equals 10 minus 0.1n. We talked about the vertical and horizontal intercepts and the slope. Now our new model is v equals 20 minus 0.1n. The observation about the difference that we made was that the vertical intercepts were going to be different. And looking at this graph, we can definitely see the first model has a vertical intercept of 0.10, and the second one has a vertical intercept of 0.20. The lines are parallel because the slopes are the same. The value of the copy card is decreasing at the same rate for both of these lines. The value of a copier card for a color copier is given by the equation v equals 20 minus 0.2n. Give a verbal description of how the graph will differ from the previous case, and discuss the practical significance of this change. So the second model we had looked at was v equals 20 minus 0.1n, where we noted the vertical intercept was 0.20, but the slope was the same as the first model. Now we're being asked to look at this model for a color copier, v equals 20 minus 0.2n. The vertical intercepts of these two graphs would be the same, 0, 20. But for our color copier, the slope is now negative 0.2, the coefficient of n. This is telling us that the value of the copy card is decreasing at a rate of 20 cents per copy. So when we look at the graphs, the graph of the new model should be steeper than the graph of the second model that we looked at. So the model for the color copier has a slope of negative $0.2 per copy, which means the graph of the line will be steeper. Than actually the first two models, because we noticed that the first two models were parallel. They had the same steepness. So let's look at a graph and talk about how the graph confirms the observations we made. So in our graph, we're going to look at the model v equals 20 minus 0.1n. That was the second model we talked about. And then our new model for the color copier, v equals 20 minus 0.2n. We noted that they would both have the same vertical intercept, and indeed they do. But we said the graph of the color copier in this line, the line would be steeper than in the graph for v equals 20 minus 0.1n, and we definitely see that in the graph. Well, let's look at all three models and see if there's any similarities or differences that we haven't talked about yet. So our first model was v equals 10 minus 0.1n. Our second model we saw was parallel to the first, but they had different vertical intercepts, different initial values of the copy cards. And then our third model for the color copier, v equals 20 minus 0.2n, had the same vertical intercept, 0.20, as our second model, but was steeper than both the first and second models. Another thing that I see looking at our first and third models, v equals 10 minus 0.1n and v equals 20 minus 0.2n, is that they have the same horizontal intercept, 100, 0, which actually makes sense if we think about our models. With the color copy card, we started out with a value of $20. In our first model, we started out with a copy card value of $10. But the color copies cost twice as much, 20 cents per copy, as opposed to 10 cents per copy. So the value of the color copy card is going to decrease twice as fast. So we started out with an initial value twice as great, $20, as opposed to $10. And since the color copy card was decreasing in value twice as fast, we end up with the same horizontal intercept, 100, 0, where we've used all of the money on the card. So let's look at another example. One evening, Lucy decided to take a bath. After letting the tap run until the water reached the proper temperature, Lucy plugged the tub and went to make a phone call. Figure 5 shows the volume of water in the tub in gallons, t minutes after Lucy plugged the tub. So in this figure, we see the volume of water in the tub in gallons as our dependent variable on the vertical axis, and time, t, since Lucy plugged the tub, in minutes on the horizontal axis. And we see that the volume is increasing. Now we're asked, what is the slope of the line? A couple of points are shown here. We have the origin, 0, 0, and we have the point 4, 30. Thinking about the slope between these 2 points, it looks like we have a rise of 30 gallons and a run of 4 minutes. 30 divided by 4 is 15 divided by 2, which is 7.5. So we can say the slope is 7.5 gallons per minute. So let's actually formally answer that. The slope of the line is 7.5 gallons per minute. Well, what's the practical meaning of the slope? Our slope we found was 7.5 gallons per minute. Looking at the graph, I can see that the line is increasing, which makes sense. Water's flowing into the tub, so the volume of water in the tub is increasing. The slope is telling us how this volume increases. So the slope, 7.5 gallons per minute, tells us that the volume of water in the tub increased at a rate of 7.5 gallons per minute. What's the equation of this line? Well, we already know the slope, so we might as well think about the equation of the line in slope-intercept form. In slope-intercept form, we should have an equation of the form v, our dependent variable, equals mt plus b. I know the value of m, that's the slope, so I have something of the form v equals 7.5 t plus, well, I need my value of b. B tells me about the vertical intercept. Looking at the graph, the vertical intercept is the origin, the point 0, 0. The v coordinate of this point is 0, so b is 0. So v is 7.5t plus 0, which of course we can just write as v equals 7.5t. So the equation of the line is V equals 7.5 T. Lucy's tub held exactly 65 gallons of water. How long after she plugged the tub did it take before water started to spill over the edge? Well, 65 gallons sounds like a volume here. So what we're interested in is, when is the volume greater than or equal to 65 gallons? So we want to know, when is V greater than or equal to 65? Thinking about our model, V equals 7.5 T, we need to know, when is 7.5 T greater than or equal to 65? To solve this inequality, I would need to divide both sides of the inequality by 7.5. Since 7.5 is a positive number, the sense of the inequality remains the same. Let's pull out a calculator to actually find out what 65 divided by 7.5 is. So here we're taking 65 and dividing by 7.5. And we get 8.66666. Looks like those sixes are going on forever. 0.66666 is 2/3. So we have T is greater than or equal to 8 and 2/3. T is corresponding to our time variable, so we're thinking of times greater than or equal to 8 and 2/3 minute. 2/3 of a minute would be 40 seconds. So anything greater than or equal to 8 minutes and 40 seconds. So the tub will start to overflow (8 minutes, 40 seconds) after Lucy plugged the tub. For our next example, we're given 4 graphs in figures A through D. Those are shown on the next slide. And we're asked to match each of the following verbal descriptions of a linear equation with its graph and label the axes. So let's look at the 4 graphs and then look at the 4 verbal descriptions and start seeing if we can match the verbal descriptions back to the graphs. So here's the 4 graphs that we're going to look at in figures A through D. We've got some increasing and some decreasing lines. And our 4 verbal descriptions. The first one is, a typewriter purchased for $600 depreciates $100 per year. The second one, an employee is paid $20 per hour plus $1.50 for each unit produced per hour. The third one, a sales representative receives a daily reimbursement of $20 for food plus 25 cents for each mile traveled. And the last one, someone is paying his mom $10 per week to repay a $100 loan. So let's go back to our graphs and think about the first verbal description. It says a typewriter purchased for $600 depreciates $100 per year. So it looks like the value of the typewriter depends on the time in years. So we can think of the value of the typewriter being on our vertical axis. We're looking for a vertical intercept of 0, 600. I can only see one of these figures that has a vertical intercept of 0, 600. That's figure C. We're also told that the typewriter depreciates $100 per year. So after a year, the typewriter should only be worth $500. And the point 1/500 looks like it lies on this line. So figure C seems to match this first verbal description. We're also asked to label the axes. Well, I mentioned that it looked like the value of the typewriter was the dependent variable. It depended on the time in years. So we can label the vertical axis with the value of the typewriter in dollars and use the variable V for that. And then the horizontal axis, our independent variable, time in years, and we can use T for that. Well, let's go back to the 3 graphs that we have left and pull up our second verbal model, which said an employee is paid $20 per hour plus $1.50 for each unit produced per hour. So it looks like this employee has a base pay rate of $20, but the more units produced by this employee, the higher that hourly rate will become. So if we think of our dependent variable as the amount that the employee is paid per hour, then we can think of our vertical intercept as being 0.20. If I look at the three figures that I have left, I see that figure A has a vertical intercept of 0.20, and figure D has a vertical intercept of 0.20. Also, both of these graphs have lines which are increasing. That makes sense for the problem because the hourly pay rate is going to increase as the number of units the employee produces increases. Well, let's think about how the hourly pay rate increases to see which of these models makes more sense. If the employee produces 1 unit in an hour, then the employee will get that base rate of $20 plus $1.50, or $21.50. If we think out to 6 units, if the employee produces 6 units, that would be an additional $9. So the employee would make the $20 base pay plus $9 for the 6 units produced. If we look at figure A and think about the number of units on the horizontal axis, if the employee produced 6 units on this graph, it looks like the hourly rate would be between 20 and 24. We said it should be 29. What about figure D? If the number of units produced is 6, well, this goes off the graph a bit, but it's definitely above 24. So let's look at figure D in a little bit more detail. We were asked to think about what the labels on the axes should be. Before we do that, let's talk about the slope. The $1.50 per unit, or for each unit produced, can be thought of in terms of slope. We can convert 1.5 to 3/2. So a slope of 3/2. If we start at the vertical intercept of 0.20 and use a slope of 3/2, then that would be a rise of 3. So rising 3 from 20 would take us to 23, and a run of 2, the 2 units. That does look like a point on the line. So I'm pretty convinced that this figure does match with the verbal description. Let's go ahead and label the axes now. So we talked about the dependent variable being the employee's hourly wage. So we can label the vertical axis as hourly wages in dollars and use the variable W or wages. The independent variable is the number of units produced. We can use N for the number of units produced. The employee's hourly wages depend on the number of units produced. Now we have 2 figures left. Let's look at our third verbal model and see if it matches with either of these figures. A sales representative receives a daily reimbursement of $20 for food plus 25 cents for each mile traveled. So if we're thinking of the daily reimbursement depending on the number of miles traveled, our vertical intercept should be 0.20. We already talked about the fact that figure A has a vertical intercept of 0.20. What about the number of miles traveled? If the employee travels 1 mile, the employee is going to have a daily reimbursement of just $20.25. If the employee travels 4 miles, 4 times 25 cents would be $1. The employee's daily reimbursement should be $20 plus an additional $1, $21. Let's look on the graph. Does it seem reasonable that if the employee travels 4 miles, the employee's daily reimbursement would be $21? That seems reasonable on this graph. We can also think of the 25 cents for each mile traveled as the slope of this line. 0.25 as a fraction is 1/4, so we can think of our rise over run as 1/4. Starting at the vertical intercept 0.20 with a rise of 1, that would just take us from 20 to 21, we'd have a run of 4, which makes sense on this graph. So let's go ahead and label the axes. Our dependent variable we talked about was the daily reimbursement that the sales representative received. That would be measured in dollars, and we can use the variable R for reimbursement. That depended on the number of miles traveled. So our independent variable is the number of miles traveled, and we can use N for that. So we're left with 1 figure and 1 verbal model. Let's make sure that this verbal model actually fits with this 1 remaining figure. Our last verbal model is someone is paying his mom $10 per week to repay a $100 loan. So if we think of the amount left to repay on the loan depending on the number of weeks this person's been paying his mom back for the loan, our vertical intercept should be 0, 100. That makes sense on this graph. The vertical intercept is 0, 100. And this person is paying his mom $10 per week to repay his loan. So after 1 week, the amount left to repay on the loan would be $90. That makes sense on the graph. After 2 weeks, the amount left to pay on the loan would be $80. That makes sense on the graph. So this figure B does seem to fit with our last verbal description. We can also talk about the slope of the graph. The slope of this graph is negative $10 per week. Looking at the graph, negative 10 we can say is a rise of negative 10 and a run of 1. So starting at the vertical intercept 100, we would go down 10, right 1. That works on this graph. Now let's go ahead and label our axes. So our dependent variable is the amount left to pay on the loan. We measure that in dollars, and we can use the variable A for amount. This depends on the number of weeks that we're paying on the loan. So we can think of our independent variable as time in weeks, and we can use the variable T again for time. Now I want to turn this over to Anne, who's going to look at some more linear modeling problems.
As promised, I'm going to work a few more problems with linear models. Here's the first one. A bullet is shot straight up into the air from ground level. The velocity of the bullet in meters per second, t seconds after the gun is fired, can be modeled by the equation v equals 550 minus 9.8t. We want to use the model to answer some questions. So the first thing we're asked to do is show that a given ordered pair, 40, 158, satisfies the equation, and then state the practical significance of this solution. So I'm going to start with the first part, just the check, first. So the ordered pairs in this problem are going to be of the form T, V. My equation is given in slope-intercept form with V as the dependent variable. So if T equals 40, as it does in the given point, let me check that V does indeed equal 158. Then 550 minus 9.8t equals 550 minus 9.8 times 40. And I'm going to pull out my calculator. 550 minus 9.8 times 40, that is indeed 158. So the ordered pair satisfies the equation. And it's the ordered pair 40, 158. Now let's think about the practical significance of this point. Just a reminder of how the variables were defined. T was the amount of time in seconds since the gun was fired. V is the velocity of the bullet in meters per second. So 40 seconds after the gun was fired, we know how fast it was traveling. So 40 seconds after the gun was fired, the bullet's velocity was 158 meters per second. Now we're asked to find the vertical intercept of the model and state the practical significance. Well, I have an equation in slope-intercept form. The constant term is the first term on the right side. That's 550. But that is the v-coordinate of my vertical intercept. So the vertical intercept which is the ordered pair 0, 550 tells me something about the initial velocity of the bullet, because t equals 0 in this case. So this tells us that the initial velocity of the bullet was 550 meters per second. Let's answer another question. What about the horizontal intercept? Well, the first thing I have to do is determine the horizontal intercept, and I'm going to do that by setting the vertical coordinate v to 0. So I'm going to need to solve the equation 0 equals 550 minus 9.8 t. Adding 9.8 t to both sides and dividing both sides by 9.8, 550 divided by 9.8 is about 56. So I got to change this to a squiggly. This is going to be about 56. So I know just about where the horizontal intercept is. So let's see what this is going to tell me. The horizontal intercept is about 56.0, and what is this telling us? Well, 56 seconds after the gun was fired, the bullet's velocity was 0. And I need to say that the bullet's velocity was 0 meters per second. Now let's discuss the practical significance of the slope. The slope in this case is negative 9.8, but we want to think about the units. Remember that slope is rise over run. So in this case, that's going to be the change in velocity measured in meters per second over the change in time measured in seconds. So we have these kind of interesting units of meters per second per second. But what this is telling us is that the bullet's velocity is decreasing at this rate. So the slope, negative 9.8 meters per second, tells us that the bullet's velocity decreased at a rate of 9.8 meters per second per second. So each second, the bullet was going 9.8 meters per second more slow. Let's consider another example. Between 1980 and 1990, the number of cable television subscribers in Pottsville increased by about 3,600 subscribers per year. In 1987, there were a mere 41,100 cable television subscribers. We want to find an equation that gives the number C of cable television subscribers in terms of the number of years T since 1980. We want to use the equation to answer some questions. So let's discuss what assumptions need to be made in order to use a linear model in this problem. Let's go back to the problem. We were told that the number of cable television subscribers in Pottsville increased by about 3,600 subscribers per year. To use a linear model, we need to assume that the rate is constant, and we're going to use a constant rate of 3,600 subscribers per year. That might not have been the exact number. It may have been a little bit more, a little bit less, but we need to make that assumption. So we're going to use, for our slope, m equals 3,600 subscribers per year. Do we have an ordered pair that we can use so we can write an equation? Let's go back to the problem. We were told that in 1987 there were 41,100 cable television subscribers. We were also given some information about what variables we should use. We were told to give the number of subscribers in terms of the years. So our ordered pairs are going to be of the form TC, and T is time since 1980. So yes, we do know an ordered pair. The ordered pair 7, 41,100 is given in the problem. So now we have a slope, we have the ordered pair, we should be able to write an equation. So let's find the equation. So we have m equals 3,600, we have the ordered pair 7, 41,100. And our linear equation is going to be of the form c equals mt plus b. The variables were defined for us in the statement of the problem. So I'm going to put in what I know. I know that the slope is 3,600. I also know that c equals 41,100 when t equals 7. So I'm going to put that into the equation to determine b. So 41,100 equals 3,600 times 7 plus b. So to find b, I need to calculate 41,100 minus the product of 3,600 and 7. I'm going to pull out my calculator to do that. So 41,100 minus 3,600 times 7 is 15,900. So I have my model. The model is C equals 3,600 T plus 15,900. But I probably should do a check. So how can I check this equation in the context of the model? Well, I was given some information. I know how many subscribers there were in 1987, and I know that the number of subscribers is increasing by 3,600 per year. So what does this mean? This means that in 1988, there should be 41,100 plus 3,600 subscribers. Well, how many is that? Do some arithmetic here. Let's see, that's going to be 44,700. So what I want to do is check to see if I get this number from my model. So my model is this. Now in 1988, T equals 8. So if T equals 8, then C equals 3,600 times 8 plus 15,900. Let's see if this equals what we'd expect it to equal. So 3,600 times 8 plus 15,900 equals 44,700. So my model makes sense in the context. So now let's answer some questions. The first thing we were asked is, what's the practical significance of the vertical intercept? Well, the vertical intercept, the ordered pair 0, 15,900, tells us something about t equals 0. Well, in this model, t equals 0 corresponds to 1980. So this point is telling us something about what was going on in 1980. Well, in 1980, there were just 15,900 cable subscribers in Pottsville. So the vertical intercept 0, 15,900 tells us something about 1980. It tells us that in 1980 there were only 15,900 cable subscribers in Pottsville. Now let's sketch a graph of the model and discuss whether or not this model could be used beyond 1990. In the statement of the problem, we were told that the number of subscribers was increasing by about 3,600 subscribers per year during the 80s. So we want to just look at from 1980 to 1990. So I know that the vertical intercept is 0, 15,900. Let's think about what's happening in 1990. So what I want to do is evaluate C when t equals 10. Well, if I look at my model, if t equals 10, I have 36,000 plus 15,900. Well, 36 plus 15 is 51, so I'll have 51,900. Now, if you want to pull out a calculator and do that calculation, you could do that as well. Now I need to label and scale the axes. So, number of years since 1980. Will live on the horizontal axis, and the number of cable subscribers will live on the vertical axis. So now let's think about a scale. I'm going to use a scale of 2 because I want to get through the 80s on my horizontal axis. So here I have 1982, 1984, 1986, 1988, 1990, and we'll look a little bit into the future, well, from the perspective of the 80s, and look at 1992. Number of cable subscribers. Well, here I have almost 16,000 and 51 or 52,000 that I need to get onto my axes. So I'm going to use a scale, I think, of 10,000 so I could get up to 60,000. 10,000, 20,000, 30, 40, 50, 60, which should work. So I have 20,000, 40,000, 60,000. This is a rough sketch, so I'm going to plot the 2 points I know and connect them with a line. So the vertical intercept and the point corresponding to 10, 51, 900, I'll plot those 2 points and attach a line. Now we were asked to discuss about whether or not we should use this model after 1990. Well, if we do continue this graph beyond the year 1990, if we could continue to use the model, the assumption is that the number of subscribers continues to increase at a rate of 3,600 per year. That might not be the case. Perhaps more and more people start subscribing to cable television. In this case, after 1990, the line would be more steep. That's a possibility. It's also a possibility that the number of subscribers will remain constant, that everyone in Pottsville has cable TV that's ever going to get it. In this case, after 1990, the slope would be 0 because there would no longer be a change in the number of subscribers. So perhaps we can use the model after 1990, but we'll have to make some assumptions in order to do that. So let's look at another example. An independent grocer made a profit of $57,000 in 1998. and a profit of $104,500 in 2003. We're asked to write an equation that gives the profit in terms of the number of years since 1990. This happened to be the year the store was open. We're told to assume that the profit increases at a constant rate. This means we can use a linear equation. And then once we have a model, we'll answer some questions. Now in this problem, the variables haven't been defined for us. So that's where we're going to start. We were asked to give the profit in terms of the number of years since 1990. So I'm going to let P represent the profit in dollars, T years after 1990. So my linear model is going to be of the form P equals MT plus B. Well, I need a couple of points to come up with the equation. Well, in the problem, I had some information. I have 2 bits of data. I know that in 1998, that would be T equals 8, the grocer's profit was $57,000. I can translate that into an ordered pair. I'm also told that in 2003, that's 13 years after 1990, the grocer's profit was $104,500. Well, I can start by using these 2 data points to find the slope. So the slope is going to be the change in profit, $104,500 minus $57,000, over the change in time, which is going to be measured in years. So the unit of my slopes will be dollars per year. I'm going to pull out a calculator to get a numerical value. So in the numerator, I'm looking at the difference, and I'm going to use parentheses to group the difference in the numerator. 104,500 minus 57,000, close parentheses, there's the difference. And I want to divide that by the change in time, which is 5 years. So this equals $9,500 per year. So I have the slope. Now I need to find a value for B. So I have P equals 9,500 T plus B. I'm going to use one of my ordered pairs to determine B. I think I'll use the ordered pair 8, 57,000 to determine B. So P equals 57,000 when T equals 8. So I have 57,000 equals 9,500 times 8 plus B. Let's make some room. So I know that B equals 57,000 minus 9,500 times 8. Let's calculate that value. 57,000 minus 9,500 times 8 is negative 19,000. So I have a model. The equation, or model, is P equals 9,500 T minus 19,000. Now I still want to check. So to check, I can use the other ordered pair and make sure that it satisfies my model. So if T equals 13, then P equals 9,500 times 13 minus 19,000. That's my model, and I want to make sure I get 104,500. So 9,500 times 13 minus 19,000 is indeed 104,500. So I've got a good model to work with. So the first thing I'm asked is, what's the practical significance of the slope? Well, the slope is positive, and we already said the units were dollars per year. So what's increasing? The profit is increasing. So the slope, which is $9,500 per year, tells us that the grocer's profits increase at a rate of $9,500 per year. Now what we want to do is consider a quick sketch of the model, because I want to talk about the intercepts of this model. So on my horizontal axis, I'm looking at the number of years since 1990. On the vertical axis, I'm looking at profit. My vertical intercept is at 0, negative 19,000. So here's a quick sketch. Positive slope. The vertical coordinate of the vertical intercept is negative. Now I use the two-color graph here because often when talking about profit, we talk about a business operating in the red or operating in the black. When a company is operating in the red, their profit is negative. At this point, they're not making any money. At this point, the profit is 0. This is where the company goes from operating in the red to operating in the black. And this is often called the break-even point. When you're operating in the black, the money you're bringing in exceeds the money that you're spending. That's a good thing. Profit is positive. This will help us interpret the intercepts. So let's state the practical significance of the vertical intercept. The vertical intercept, 0, negative 19,000, tells us that in 1990, the grocer's profit was negative $19,000. What does that mean? That is, he was in the hole 19,000 bucks. Probably some sort of costs of starting up a business. What about the horizontal intercept? Well, the first thing we have to do is determine the numerical value of the horizontal intercept. Horizontal intercept, the profit's going to be 0. So I need to know where 9,500t equals 19,000. So t is going to be 19,000 divided by 9,500. 19,000 divided by 9,500 is 2. We probably could have seen that coming. So the horizontal intercept is the point 2, 0. What does it tell us? The horizontal intercept, 2, 0, tells us when the grocer's profit was 0. So 2 years after 1990 is 1992. The grocer's profit was $0. That is, he broke even. So that's the end of Lesson 20. It's also the end of the Math 60 telecourse.